Let's do section 11.2, page 552, exercise 39, which reads, the velocity v of t of a particle moving in the plane is given, along with the position of the particle at time t equals 0. Find A, the position of the particle at t equals 3, and B, the distance the particle travels from t equals 0 to t equals 3. And for exercise 39, v of t is equal to 3t squared minus 2t, comma, 1 plus cosine pi t, and our initial position is 2 comma 6. So let's start with part A. And if v of t is equal to dr dt, then if we're given v of t and we're trying to find r, we should be able to do the inverse of taking a derivative, which is, of course, taking an integral. So that means that r is going to be the integral of v dt. Now, again, because the x and y components are separate and independent, we can integrate each component of v of t separately. So we can say that r of t is going to be the integral of the x component. So that's going to be 3t squared minus 2t dt. And then the y component of r is going to be the integral of the y component of v, which is 1 plus cosine pi t dt. And we can just integrate term by term here. So this is going to give us, for the x component, 3t cubed over 3 minus 2t squared over 2 plus a constant, which I'm going to call c1. And then to find our y component, we're going to integrate term by term over here, and we're going to get t plus 1 over pi times sine pi t plus a different constant, c2. And to figure out what these constants are, we're going to use the information we were given at the beginning, which is the initial position. So this is going to be r of 0. So we're going to go down here, and we know that r of 0 means that we're going to substitute in 0 every place that we see a t. So this is going to be 0 minus 0 plus c1. This is going to be 0 plus 0 plus c2, and that has to be equal to 2 comma 6, which is going to tell us that c1 is equal to 2 and c2 is equal to 6. And now we can rewrite our expression here for r. So r of t is going to be t cubed minus t squared plus 2 for the x component, comma t plus 1 over pi sine pi t plus 6 for the y component. And part A really asks us to find what the position vector is going to be when t is equal to 3. So that means that I'm just going to substitute in 3 everywhere. So I'm going to have 3 cubed minus 3 squared plus 2, comma 3 plus 1 over pi times the sine of 3 pi plus 6. And then I can do some algebra to simplify this. And I'm going to have 27 minus 9 plus 2 for the x component. For the y component, I'm going to have 3. This whole thing is going to go to 0 because the sign of any multiple of pi, any integer multiple of pi, is going to be 0 plus 6. And we're going to end up with 20 comma 9 as our position when t is equal to 3. Now, part B asks us to find the distance the particle travels from t equals 0 to t equals 3. So I'm going to go to a new page here. And if I'm talking about the distance traveled, then I'm talking about the length of the curve. And so what I'm going to do is take the integral from a to b of the magnitude of the velocity as a function of time times dt. And so this is going to give me the integral from a to b. And to find this magnitude, I take the square root of the sum of the squares of the components and integrate that with respect to t. So our integral is going to go from 0 to 3 because we are interested in the time interval from 0 to 3. And I'm going to have the square root of, and I'm going to take the x component of the velocity, which is going to be right here. So that's going to be 3t squared minus 2t, and that whole thing is squared, plus the y component squared. And this is going to be the y component of the velocity. So it's going to be 1 plus cosine pi t squared times dt. And I don't think that that's going to be very easy to integrate. So I just used my calculator and I used FNINT and I got 19.343 as the distance the particle traveled.